Hello, I'm Daniel Cross, Principal Solutions Architect for Cadence Design Systems, focused on mixed signal verification solutions. I'll be talking right now about SystemVerilog real models for in-memory computing. Talking about in-memory computing, which is variously abbreviated as IMC or CIM or perhaps some other arrangements of those particular letters. Of course, I'll have to explain how it works, but I'm going to come at it backwards and first describe the machine learning applications and why it's useful for those applications, and then get into at least one implementation of how to build it. Based on that description, we can look at whether it's in fact a mixed signal type circuit, and then look at a way to model it that is efficient and useful for system simulations. First, a crash course in neural networks. A neural network that's used for machine learning, or also known as computer inference, consists of a bunch of nodes that are arranged typically in layers, and each node in a layer is connected to multiple nodes of the layer next to it, and each of those connections is associated with a weight. So the output of a prior node is multiplied by a weight, and then all the results of those multiplications are summed at each node, and then each node generates its output based on that summing. Of course, at the input, there's some input vector and an output vector that gives you some idea of either classification or solution of a problem that is the reason you are using a neural net to begin with. For some additional introduction to neural networks, check out Paul McClelland's blog Breakfast Bites, particularly the entry about why Google is so good at recognizing cats, and his summary of the Embedded Neural Network Summit, where he gives a condensed overview of what neural nets are, what they're good for, more than I can go into here, and also points to other resources. Really, you should read Paul's blog every day. He always has a wealth of interesting information about the entire electronics industry. Focusing in on a single neuron, here we have our inputs are going to be x sub j's, and they're going to be multiplied by these weights, which are weight kj, k being the index of the neuron in a particular layer, and then all of those multiplications get summed in the neuron, and often there's a bias applied as well. And finally, the output of the neuron gets passed through what's called an activation function, which is some nonlinear function. Much like a neuron in a nervous system has to pass a certain threshold before it will fire. Mathematically, the neuron equation is going to be a sum of all of its input weights times the input vectors, which would be either the outputs from the nodes of the previous layer or the actual inputs, with the activation function applied to the resulting sum. The summation there is a multiply and accumulate, also known as MAC or MAC. And to do computer inference, a neural network has to do many multiply and accumulates in rapid succession. And there is special dedicated hardware and graphics processors that ends up being very, very good at doing those multiply and accumulates in very rapid time. And what you often find is that the limiting factor in performance becomes the cost of moving data around. Doing a little bit of research, there are some wide-ranging estimates of the cost of energy per memory access, ranging from 20 picojoules per bit up to perhaps 10 or more nanojoules per access. And notice that these energy figures are not given for the same size access every time. And of course, there's going to be some difference between a read access and a write access. Additionally, there will be some variation with process node. And when you start multiplying these access energies with the number of neurons in one layer of a neural network, which could be in the thousands or even tens of thousands, it really starts to add up. So if you can save that energy by doing the math in the memory, you could potentially increase your performance drastically. And this is where in-memory computing comes in. We'd like to do these multiply and accumulates on the data that's resident in the memory. Most strategies for doing this rely on the structure of SRAM bit cells, treating them as tiny 1-bit multipliers. And there's several strategies for doing this. We're just going to focus on one for our modeling efforts. Here's an SRAM bit cell. It is a regenerative latch, which is coupled to bit lines, which provide input and output for data. And access to those bit lines is driven by a word line. And the operation of this is that assertion of the word line causes any data that is being forced onto the bit lines to be stored in the latch. Similarly, if the bit lines are undriven, asserting the word line allows the latch to drive the bit lines to the value of whatever data is stored in it. Now, if instead of driving the word line completely on, we place it at some voltage that puts the devices M5 and M6 in their active region, then we'll get a partial driving of the bit lines by the contents of the latch. And the current coming out of them will be proportional to the gate voltage on M5 and M6. So if we drive the word line with an N-bit DAC and then measure the current coming out onto the bit lines, we effectively have an N by 1 multiply of the DAC input by whatever is the content stored in the bit cell. Note that if the content of the bit cell is a 0, the current will be actually flowing into the bit cell from the bit line. And if it's a 1 stored in the latch, the current will be flowing out of it. So then to turn this into a complete multiplier, we just need an array of bit cells, which is what a memory is. We can apply some current sources at the tops of all the bit lines, so that we provide some bias current to feed the zeros, and then we collect current out from the ones. We can drive each row with a DAC value to provide an input vector, and each row gives us a value of, in this case, n bits. And if we assume the DAC resolution is j bits, we've got each row doing a j by n multiplication, and then we sum them up on the vertical axes by allowing all the currents to add up and dropping them across a resistor at the bottom of each column. And then we can read out the value for each column with an A to D converter. And if we assume the A to D resolution is k bits, we can get an n by k output word that is a complete value of the multiply of the DAC values by the row value that is stored in the memory. And that gives us our Nernst equation. I hope I don't have to work too hard at this point to convince you that this is, in fact, a mixed signal circuit. We've got D to A converters, we've got A to D converters at the output, we're summing currents, and if we want to simulate it with any kind of accuracy, we need to use some kind of mixed signal technique. Now, we could do it completely at the device level with transistors and resistors and capacitors. That's going to be very slow. It'll certainly allow us to do design and perhaps do some trade-offs between speed and power consumption at the device level. However, to make system trade-offs or make decisions about our system architecture, we need something that's going to simulate much faster, because you'll never get through a complete inference cycle using a device level model and forget about training. So we're going to build a SystemVerilog real number model for this subsystem. We're going to make use of SystemVerilog concept of user-defined nets. We'll be using an electrical equivalent net to model the bit lines, which we'll describe a little bit later. But first, we need a way to model that word line. And we're going to do it with a custom-built user-defined net type that is going to be a structure that just has one enumerated value. And the system we're going to model here is going to use 3-bit DACs to drive the word lines. So each DAC has got 8 states, and each state is going to get a separate enumerated state. And then there will be an off state for completely off and an on state for actual writing and reading the bit cell contents. And we also put in a resolution function just in case there's an opportunity to have multiple drivers on a WL net. However, we don't really use that in this model since each line just has one DAC driving it. In a real system, it's possible that there would be a DAC for driving the analog states and a line driver for read and write. And if that's the case, the resolution function would need to be used in that case. Diving all the way down to the bottom, Looking at the bit cell, we can see we've got electrical equivalent nets for modeling supply and ground and those bit lines. We've got a WL net for the word line and logic for a write enable and a read enable, which were not pictured in the previous slides. The addition of these signals really simplified our model building. But I do think there are genuine reasons why you might want those signals in a bit cell because of the non-zero rise and fall time of the D to A converters. They would make the bit cell a little bit bigger, so there's good reasons not to use that as well. We will see their function in our bit cell in just a few minutes. One thing we did in the bit cell model was make sure that we can account for different current drains in different states of operation. So we set up 3 parameters. One is a leakage current, which is always going to be occurring whenever there's power. We have a current for when it's actually doing a calculation. In other words, when the word line is driven to one of the analog states. And we've got write current for when the word line is full on and the bit cell latch is either being written to or read from. And we've got a variable, I supply, that keeps track of all the currents that are in use in the bit cell. And those get assigned to the supply and ground. And at the top level of the simulation, the current drains for all of the bit cells and all the DACs and the A to D converter all get added up, and we can see the power consumption of our multiplying memory unit in a dynamic fashion. The bit cell's got a logic value that actually stores its content. Of course, it's going to be X when it starts up, or if power ever is removed. And then we have a vector that represents the potential leakage from the bit cell, and it's going to be indexed by the integer value of the enumerated element of the write line net for when we're doing multiplications. Depending on the DAC value on the word line, you get a different amount of leakage into or out of the bit cell. And we'll see in a slide how that works to provide the input or output current onto the bit line. The main functional loop of the bit cell is going to be sensitive to a rising edge of the write enable or read enable lines. And what it does is going to depend on the value of the word line. For word line, state of off or X, we want the bit cell to be in standby. So the bit line currents are not going to be driven, and the total supply current is just going to be a little bit of standby leakage current. It'll be in a direct write or read if the word line state is fully driven, in other words, on. And for a read, we just set either a full scale current output or input so that the bit line gets driven to its full on or off state, determined, of course, by the content stored in the bit cell latch. And while it's in that mode, the bit cell supply current is going to be set to iCalc. And for a write, the content stored in the latch gets set to a 1 or a 0, depending on the voltage that is being driven on those bit lines. And of course, in that mode, the bit cell supply current is going to be iWrite. And if the word line is in an intermediate state, the current on the bit line gets set by indexing into that scale factor variable. And that's multiplied by plus or minus 1, depending on the contents. The bit cell supply current for this mode is iCalc. And when the write enable read enable goes back to 0, we go back into standby and we just have a leakage current present in the bit cell. Finally, the actual bit line gets set with the current that we stored previously. And we also got a bunch of checks that make sure that its supply and ground are in a good state. And if they're not, the latch content gets set to X. Our DAC model has got, as I mentioned, a 3-bit input. And its output is that WL net type. And we've got an input logic that causes it to generate a strong drive for the word line for reading and writing. We're going to track the internal state of the DAC with an enumerated variable that's going to match the definition of the WL net. And ultimately, that gets assigned to the output of the DAC once we determine its value. The DAC has got similar logic to what's in the bit cell for checking the supplies and making sure that they're in the correct ranges and determining whether the DAC should be on or not and setting the current drain appropriately. As we'll see, the DAC supply current has got two components. One is a background current, which is set to an active level whenever the DAC is enabled. The other is a variable part, which changes depending on the activity of the DAC. Here's the main DAC function that sets the internal state of the DAC. We have a parameter there at the top, which is iSettle, which is going to be the current drawn by the DAC while its output is changing. And if the DAC state is a driven state or an analog computation state, we're going to set the variable iChange to the settling current, and that current will last until the DAC is settled, which we've coded here to be 10 picoseconds. And that'll happen every time the internal DAC state changes, either to a dry state or to an analog state. And essentially, whenever an input to the DAC changes, we're going to determine whether the DAC is on or off. And if it's called for, we'll have a pulse of change current. Now, how we envision the circuit is going to be realized and how we built the model is that if the DAC is supposed to be driving the word line either full on or full off, then the WL drive input to the DAC needs to be driven, and for analog computation, it should be undriven. So for the case of WL drive equals 0 or equals 1, we set the DAC internal state appropriately, and we also set the change current either to 0 for the off state or to the settling current for an on state. And naturally, for analog computation, then we'll set the internal state based on the 3-bit DAC input, and the iChange current variable will get a pulse of settling current. And ultimately, the contribution to the supply and ground nets are just going to be the background supply current, which is always there whenever the DAC is in operation, plus whatever the settling current is stored in the iChange variable. And of course, the DAC internal state gets assigned to the DAC output WLnet. So now we've got our basic components. We need to build them up into a memory structure. First, we build a row structure, and we have the number of columns in each row as a parameter. Here we're setting it to a default of 8. And we're just going to use a generate to create a row of bit cells that are number of columns wide. And you can see that they all share a word line, but each column has got its own bit lines, which are indexed by the genvar. And then we build up those rows to make an array. You can see there we pass in the parameter of row and column. And of course, the columns just gets passed on to the row element. And the row elements get instantiated here, along with a DAC to drive that single word line, and all the word lines. Then the DAC inputs get indexed by row with the genvar. The bit line input drive is assigned by column. So in that same generate loop, we can put our resistive terminations, which is just going to be a VR source G element, which is a grounded voltage and resistance E net element. And we're not going to set a voltage on it. We're just going to use it as a resistor. We are going to measure the currents there just for testing purposes. And those will be assigned to a pair of arrays, IBL and IBL bar. In this case, we did not model the current sources at the tops of the bit lines. That is definitely a planned enhancement for future versions of this model. For now, we're just going to live with negative voltages on the bit lines. And as our A to D readout, we're just going to use a 1-bit A to D, and we're going to therefore get an 8-bit multiply and accumulate result. And that way we can use the same A to D converter when we do a full memory read as well. Now I'll flip over to Linux and we can see this model in operation. All right, we'll go ahead and run this. At the top here, we're looking at our supply EENet, and we will actually be able to see the instantaneous current as the memory goes through its various modes. So I'm going to go ahead and run this. Remember, this is up to 5,000 clock cycles, and that's how fast it runs. First, I will focus on the initial write-in. You can see every time we write to a row of bit cells, we get a pulse of current. And this is the data that's being written in. You can see row by row, it's just random values that came out of the randomize. Looking down into a bit cell, we can see that when this particular bit cell got written to, its content changed from the default state of X to a 1 as the 1 was written in. And our word line state went from off to on and then back to off as we were primed for writing. The next event is the multiplication. We'll go ahead and zoom in on that, and that's a single event. It takes a lot less time than the writing. And this is just a demonstration of the overall power saving you get by using a in-memory computing circuit. You don't have to move the data around. That's really what takes the time and the energy. So in this case, deep down in the bit cells, our word line for this particular row got set to the value of B for that row, which was the state S2. Yes, so that's row 0, and the one below it is row 7, and it's getting set to a state of S0. And it all depends on what the B value was for that row. The DAC is putting out that value, and it goes down into the bit cell, where we'll see that depending on the value of the contents and the value of the DAC output, we get a different amount of current being driven onto that bit line. Here, for example, row 0, column 0, the content was a 1. The value being driven in was a 2. And so we get a positive 20 microamp current flowing out of the bit cell onto that bit line. And of course, the bit line sums up all the currents and ultimately produces a voltage, and that's the EEnet resolving the voltage based on all the currents multiplied by the resistance at the bottom of that column. That particular column 0 bit line ended up as a 0.078 volts when all of the currents were added up. And with all of the columns summed up like that, we can look at our output result. Essentially, what we're going to see here is that if BL for a given column is positive and BLB for a given column is negative, that's going to get sliced as a 1, and the opposite's going to get sliced as a 0. So looking at these values here, we can see reading down the column, we've got a positive, a negative, positive, positive, and so forth. So this is going to get parsed as 1, 0, 1, 1, 0, 1, 1, 1. And we can see looking at the BL bars that they're all opposite that. There's no surprises there. And so that is going to get sliced as a B7. And that is the result we get out of the memory. And as the simulation goes on, the A matrix value is retained in the memory, and a sequence of random B vectors is multiplied into it. And if we pick out a single bit line, sometimes on that bit line, the currents end up summing to a positive, and sometimes they sum to a negative. And the voltage that you get when pushing that current across the resistor varies accordingly. And we get out a series of 8-bit results, seen here. And those values, along with the A and B values, are dumped to the log file by display statements. We can see all of those numbers looking at our console output. So here's our A value that we started out with. Here's our initial set of B vectors. And in that case, the multiplication result ended up being a hex 87. And of course, for each multiplication, there's a spike of current, and we can actually go through and keep track of those and get a total energy per multiplication and get a good estimate for our system of what kind of power consumption we're going to see in an actual machine learning application. In this video, I've tried to present a case that in-memory computing can save power in machine learning applications. I also tried to make the case that IMC circuits are by nature mixed signal and therefore can be modeled using real numbers in SystemVerilog, and that those real number models of IMC circuits can capture very fine details of behavior, including any current summing behaviors, analog delays, also peak and average power consumption. I presented to you an example of a real number IMC model, described its code and its operation. And one thing we noted was that the real valued IMC model simulated very, very quickly, which meant that it's definitely scalable and a much larger model could be included in a machine learning system simulation and be fast enough to obtain usable results. Gracious thanks to these and many more authors. The database for this entire example is available on our support portal. You'll need a Cadence support account. If you don't have one, just call your Cadence representative. Thank you for watching.